review. So this is, again, 7.1, linear and nonlinear systems of equations. We start out with some very basic things that you are already familiar with, so that should make you happy. We're going to use the method of substitution to solve systems of linear equations, not always the most desirable. We'll use the method of substitution to solve nonlinear systems of equations in two variables. We'll use graphical approach to solve systems of two variables equations, and we'll use systems of equations to model and solve real life problems. So first is the method of substitution, and like I said, this should be pretty much a review for you, at least for the linear. I'm not sure if we've done nonlinear systems, but the substitution method will work. A lot of times we use the substitution method when we have two variables, two unknowns, and a lot of times the coefficient of one of those variables is 1. So most problems have involved either a function with one variable or a single equation with two variables. However, many problems in science, business, and engineering involve two or more equations and in two or more variables. And so our goal is to get past two equations and two unknowns. So this is a system of equations. If you were going to solve this, and my preferred method is generally the elimination method. Do you kind of remember that? It's not, it's where you would maybe multiply both equations by, like if I wanted the x's to drop out here, I'd multiply the top equation by 3, the second equation by -2, and then when I add those two, the x's would drop out and I'd decide what y is. A lot of times though that when one of the variables has a coefficient of 1, we can get that variable alone and then substitute that in, and that is going to be our substitution method as we go. And here they're just giving you the answer. This order pair 2, 1 is a solution, and then you can kind of just check through to make sure. So we'll look at 4 ways to solve systems, and the first method is the method of substitution. And sometimes it's a good method if one of the variables, again, has a coefficient of 1. Sometimes it can get fraction intensive, so it's not super desirable, but we do want to know it so that as we move forward and do other things, we know how to do this. So this should be familiar to you. So you solve one of the equations for one variable in terms of the others. You substitute the expression that you found into the other equation to end up with an equation with one variable. You solve that equation, so you get that variable, and then you back substitute. Maybe that terminology we haven't used a lot, but that's what it's called when we back substitute. We're going to take that answer that we have and substitute it back into the other equation to find that other variable. And then we want to check that it satisfies each of the original equations as we go. And so here's our first system, and we will do this one just to kind of brush up and remind ourselves of what we're doing. It might seem unusual to you that I'm going to write out my steps, but I am going to write them out because you'll find that that might be desirable as we will move into things like this, 4 equations and 4 unknowns, okay, instead of 2 equations and 2 unknowns. So here, it's essentially the same procedures, but just, more involved with more variables. So step 1 is to solve for one variable in one equation, and I'm just going to do the x plus y equals 4, and I'm going to solve for y. Y is 4 minus x. Then my step 2 is to just substitute that in the other equation. So it's x minus y equals 2. I'm going to put in place of that y the 4 minus x. Please do be careful because people do still get these wrong. I know I'm saying that this is review and things that we've done before, but it's very common for people to make little mistakes as they go. 0. So that has to be distributed through x minus 4 plus x equals 2. So 2x minus 4 equals 2. 2x, when I add 4, is 6, and x is 3. So once I get x equals 3, then I'm going to back substitute. Truly, you can back substitute in anything, but if I've already gotten that y variable set alone, I might as well use y equals 4 minus x. So y equals 4 minus 3, and y is 1. And so that gives me my answer of 3, 1. Then to check that, I take my two equations, 3 plus 1, and see if that's equal to 4. Yes, it is. And 3 minus 1, and check to see if that's equal to 2. And yes, it is. So, that's the procedure, and it should be very familiar to you, correct? Okay. So now we're going to kind of move on, and let's see. The term back substitution implies that you work backwards. I'm just going to kind of make a note of that again, because we're maybe not used to that terminology as we go. So here's a problem that we might have to do. So the total of $12,000 is invested in two funds paying 5% and 3% simple interest. Recall that the formula for simple interest is I equals P times R times T, where P is the principal, R is the annual interest rate, and T is the time. And the yearly interest is $500. How much is invested at each rate? So here the challenge is to come up with your two equations. And so it says how much is invested at each rate. So do you agree we have two rates, right? So two amounts that we're trying to find. So I would let x equal the amount invested at what percent? 5%. And then y would be what? 3. The amount invested at 3%. Oops, 3%. So, what are some relationships here? What's an equation you can come up with? What? Say that again? Well, the total that we're investing is $12,000. Well, no. Let's kind of go back a little bit here, and think about how we're getting these numbers. So ignore the I equals PRT a minute, okay? And let me just ask you this question. So if X is the amount invested at 5% and Y is the amount invested at 3%, so those are the amounts that you're putting in at the very beginning, correct? And what is the total amount that you are investing? $12,000. And so how are X, Y, and 12 related? When you do what with them exactly? Yes, X plus Y equals 12,000. Do you agree with that? So kind of think that through. So X is the amount invested at 5%, Y is the amount invested at 3%, and the total amount we're investing is $12,000. So that gives us our first equation of X plus Y equals $12,000. So that's a relationship. So if X is nothing, Y is 12,000. If X is 6,000, Y is 6,000, right? So they are definitely related in that way. Now I want to talk about interest rate. So if I put this this X amount in, and and it says the yearly interest is $500. So principal equals, or interest equals principal times rate times time. Interest equals principal times rate times time. So do you agree right now they're telling us our time is 1 year, correct? And our rates, we have them for the two different amounts of money. And the principal is how much money for this pot. How much money are we putting in this pot? Or what represents the money we're putting in that pot? X, right? So we're putting in X dollars, and what's our rate? Oh, so as a decimal, 0.05. And so if I wanted to know the interest on this money, I would take X times 0.05. Do you agree with that? And if I wanted to know the interest on that money, what would it be? What times 0.03? Y, right? Y times 0.03. And if the interest here I'll try to squeeze it in here, 0.05x, oops, and the interest here is 0.03x, I think so. So 0.05x plus 0.03y equals 500. Do you agree with that? So, oh, this one, yes, my bad. Yeah, and and that one doesn't even really look like an X. So that's an X and a Y. So think about, we had to come up with our equations now. X plus Y equals 12,000. 0.05x plus 0.03y equals 500, and make sure that we kind of know what that relationship is. Now, I'm going to tell you, because I don't do a lot of things with a calculator and I do them at the board, this is hard for me to manage. Do you agree? Just because it's a lot of decimals and everything. I personally would take that equation and multiply every term by 100. Does that make it an easier equation for me to look at, do you think? 5x plus 3y equals 50,000. 50,000. And so, do you have to do that? Not necessarily, right? But, to me, is it okay if we do that for me or not? So I'm just going to say, for um, ease of working the problem, I'm going to multiply 100 times 0.05x plus 0.03y equals 500, and I'll get 5x plus 3y equals 5,000,000, 50,000. So that, and I'm writing that because we have people who are not here today. So then my two equations are this one and this one. And so step one, what variable would you get a loan in which equation? Yep, y equals 12,000 minus x, and then we've got 5x plus 3y equals 50,000, and so then we put this in for that y, 5x plus 3 times 12,000 minus x equals 50,000. So take a minute, find x, find y. How much at each percent interest rate? And part of what we want to do is be able to communicate our mathematics as we go. And so did you get x equals 7,000? Okay, so x equals 7,000 dollars it would be. What will y be then? What was it? 5,000, because it's y is 7,000 or 12,000 minus 7,000, which is 5,000. And so then we want to be able to say that I'll just put x equals 7,000 there. And so we're going to invest $7,000. So part of this is communicating the answer, and I do remember already, just in going through this problem, that I will be asking you to give like a sentence in these as we go when it's a word problem type thing. So we're going to invest $7,000 at what? At 5% and $5,000 at what? 3%. So just kind of be ready to not just give, oh, X is this or Y is that, but also to kind of give a kind of something about this. So nonlinear systems of equations. So the trickiest part of nonlinear systems of equations is kind of to decide which variable to get a loan and which equation. And because now it's not just a matter of having fractions, but we might also have powers of x or y, or roots, or logarithms, or trigonometric equations, or things like that as we go. So the equations in example 1 were linear, and substitution can be used for systems that are nonlinear. So here's our next system. As you're looking at it, kind of think to yourself, which equation should I solve for a single variable, and which single variable should I get a loan? So, what do you think? Yes, I agree. I want to solve the bottom one for one variable. Which variable do you think I should solve for? Why? Correct. And I'm guessing you're not asking me why. So we want to get y alone. Because think about, even if I get x alone, then I would have this expression with y. I'd have to square that, FOIL it out, and do all that. In this one, it would be very difficult to get x alone. The only thing I can think of, I'd have to maybe complete the square, and it's just going to be kind of a mess to do that. So that's kind of one of the big things for this one. And so that's what we're going to do. So we're going to use this second equation, and we're going to get y alone. And so y is going to be, what is it going to be? 2x plus 1. Did I do that right? Help me figure that out. 2x plus 1 is equal to y. I was gonna say I cheated, but I didn't really cheat. But I kept the 2x here. I moved the y over there and the 1 over there. So 2x plus 1 is equal to y. And then I'm gonna substitute that in. So I have 3x squared plus 4x, minus y. It always helps if you write the equation correctly. So if you don't, that's always a bad thing. And so we'll just plug that in. So we get 3x squared plus 4x minus, and do be careful because minus parentheses 2x plus 1 equals 7. And now we have to solve this. And this is just, an algebraic manipulation problem. And it's going to be squared, so we're just going to have to 3x squared plus 4x minus 2x minus 1. Oops. Wow, I was going to do my arithmetic wrong. Minus 1. Can I do this minus 7? Because I feel like I'm going to get one side equal to 0. So I have 3x squared plus 2x minus 8 equals 0. So you take a moment, figure out what x is. And I'll look at them. That one I'd look at again. So whatever method you use, and I really just use guess and check, 3x squared has to be 3x and x. 8 can be 8 and 1 or 2 and 4, and my middle term is a 2. And so if I put a 2 here and a 4 here, I'm going to get 6 and 4. That's going to give me 2. This I want to be positive. Oh, I'm sorry. Wow, I don't know why I wrote x squared there. 3x and 3x squared has to be 3x and x. And when I FOIL that out in my head, 3x squared plus 6x minus 4x gives me 2x and minus 8. So x is 4/3 or x is -2. So I get those two values. Now I'm going to go back up here and really I'm going to just put that right in there, correct, to get my y. And so y is 2x plus 1. And when x is -2, y is 2 times -2 plus 1. So y is -4 plus 1, so -3. And then when x is 4/3, is that correct? 4/3, then y is 2 times 4/3 plus 1. So that's 8/3 plus 3/3. And so that's 11/3 is how I would categorize that. 4/3, 11/3, and -2, -3. And then always, a good idea to check as we go. And, maybe one is easier to check than the other. -2. So 3 times -2 squared plus 4 times -2 minus -3. So let's see what that is. 4 times 3 is 12, right? So I've got 12 plus 8 plus 3. Oh, I must have done something wrong. Oh, that's -8, I think, right? and then plus 3. So 12 minus 8 is 4. 4 plus 3 is 7. So that works in that one. And then I'll do it here. 2 times negative 2 minus negative 3 is negative 4 plus 3 is negative 1. So that works. So that one checks out. The 4/3, 3 times 4/3 squared plus 4 times 4/3 minus 11/3, oops, is, let's see, what is that? 16 over 3. Yeah, but then I'm canceling one of those. Is that all right? So 16 over 9, and then I'll cancel that. So that's 16 over 3 plus 12 over 3 minus 11 over 3. So 16, I'm going to go 12 minus 11 is 1. So that's not going to be right. Did I do something wrong? Where are you? Whoa. So, no, I think x is positive 4/3. Okay. So, yeah, these are the factors. And this is x equals negative 2. And negative 2 did work for us, but I must have something wrong in my 4/3. Where, where am I? No, 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 no. Okay, wait. Let me back that up a second. So yeah, the factors are right. So wait, let me just kind of 4x minus or 3x minus 4 and oops, x minus x plus 2. And so when I distribute that times that, it's 3x squared plus 6x. And then when I multiply this times these, it'll be minus 4x and minus 8. And then this will be 3x squared plus 2x, oops, and then minus 8. And so that's what I want, and this is what I want. And my 4/3 should be right. I maybe just have an error here. Let me kind of just figure out what it is. Oh, 16. 4 times 4 is 16. Oh, that's where it is. Yes. So there's my error. And then 32 minus 11 is 21. Oh, thank heavens. It's 21 over 3. And that is 7. So that one checks. Wow. And then the other one is 2 times 4/3 minus 11/3. And this is 8/3 minus 11/3, and that's negative 3/3, and that's negative 1. So it does check out. So both of those answers check. And so that was a little bit of a more of a mess than I expected, but we did get it to, we do get that to work out. And so that is the concept of solving that nonlinear systems using substitution. And I will say that a lot of times substitution is a kind of good method for that. Let me look, and I'm hoping I have a, oh, do not. Um, so now I want you to think about this. If you have two linear equations, and by the way, this had two solutions, correct? So kind of think about the fact that this might be something parabolic, right? Have some kind of parabolic, and this is something linear. So if we have a parabola and a line, they can hit at two spots, right? Whereas when we've had always linear systems of equations, they only hit at one spot as we go. And excuse me. So the next thing I have is just a question for you. And I am going to give you a little piece of paper to answer on. So I'll do this dark purple today. And I want you to draw some pictures for these as well. Oh, maybe I should have given you a half sheet of paper, but oh well. I don't remember. Let me see how many there are here. Just a second. We're not going to do that one. Ooh. Um, so how many possible solutions are there for the following systems? Linear and two linear equations. And so I'll answer this one for you. If I have two lines, they can intersect at one point, correct? What else can they do? Not intersect. One other thing they can do. Um, Perpendicular would still be one. They can be the same line, right? And so this is one solution, no solutions, and an infinite number of solutions, right? So now, do the same thing for linear quadratic, linear cubic, linear circle, and quadratic quadratic. See what you can come up with. Cubic is kind of, yeah, like that. Cody, on that little piece of paper, the question is how many possible solutions are there for the following systems and show graphically. So we did the linear one together. If you have two linear equations, they can intersect in one point, no points, or an infinite number of points. So let's kind of just see what we've got for these. And I just wanted you to kind of think it through before we went over it together. So if it's a linear and quadratic, what could it have? It could have one linear quadratic. So maybe like that and like that, right? So one. What else could it have? Two, like that, right? And none, right? Zero, like that. Linear cubic. One. It could have two. So I'm going to do it this way, kind of. Do you agree? So it could have two. It could have three, right, like that. Um, how's it having none? Yeah, yeah. So, yeah, it's going to have something. Linear and circle. Zero, circle, linear. Two, and one. And quadratic, quadratic. Zero, maybe like that, right, or something. Oh, I didn't write 0, 2, and 1, and that was 3. I'm sorry, 1. So maybe like that. Oops. Oh, well, that's as good as I'm going to get for 1. What else? 2, like that, maybe. Oh, which that one doesn't really look quadratic, but okay. And infinite. So if they kind of map on each other, infinite. Right? So that's kind of, something to just file away in the back of your mind, because we're used to linear, linear just being this way, 1, 0, or infinite, and now we're looking at things that could have, other options as well. So here's a system for you to solve, and I tried typing it, so it's a little small. So negative x plus y equals 4, and x squared plus y equals 3. So try that by yourself and see what happens. I'm going to give you a hint that it's not going to factor, but you have a way to solve a quadratic if it doesn't factor. Yeah. I do want to go over this one, so I'll maybe just kind of start. Did you use the first one and get y alone, probably, right? Oh, Ooh, I don't know. Maybe I'm going to buy something at the I think I accidentally tapped that little icon there. So if I use that first equation, y equals x plus 4, and then x squared plus y equals 3. In place of that y, x squared plus x plus 4 equals 3. So x squared plus x plus 1 equals 0. And do we agree that did not factor, correct? And so what are you using? X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. What did you find? Oh, plus or minus. 1 minus 4, negative 3. So what does that mean? Okay, so we're going to say that there is no real solution. And so what does that mean about this parabola and line? They do not intersect, right? I mean, we don't really know just by this what they look like, but essentially they do not intersect at all. And so just be kind of aware of things that can happen there. And then we are going to look at the graphical approach to finding solutions, which will be you know, it's always our least desirable when using linear equations, but sometimes when we're using nonlinear equations, like logarithms, which we will be doing tomorrow, then, you know, graphing it might be a good idea to kind of get a sense of where everything is. So that is it for today.